Welcome to the Deep Dive. We're here to take complex topics, break them down, and really give you the insights you need to be well-informed. Today, we are plunging into the world of artificial intelligence, specifically how we're making those, really powerful language models you might use every day much more efficient, and crucially, doing it without sacrificing their quality.
That's the goal. We're looking at a really fascinating new framework today. It's called Mixture-of-Recursions, MORE for short. It comes from a paper, Mixture-of-Recursions, Learning Dynamic Recursive Depths for Adaptive Token-Level Computation. Quite a title.
Yeah, often are.
But the core idea is pretty elegant. It offers a novel way to deal with those, well, huge computational and memory costs that come with large language models.
Okay.
So our mission today is really to unpack how this MORE framework manages to combine two key efficiency tricks, let's say, to make these models more powerful but also more practical to actually use.
Right, because to really get why Moore is innovative, we need to understand the problem it's solving. The big challenge. We've seen these models scale up massively, billions of parameters, and they can do amazing things. But that scale, it comes at a cost. Huge memory needs, massive computation. It makes training them or even just running them outside of, specialized data centers really, really hard. It's a major bottleneck.
It absolutely is. And traditionally, efforts to make them more efficient, they've tended to follow one of two paths. Path one is reducing or sharing the model's parameters, its internal components. That's parameter efficiency.
Okay.
Path two is being smarter about compute, spending more processing power only when and where it's truly needed. Adaptive computation.
So parameter efficiency or adaptive computation.
Right. And the real challenge, the tricky part, has been figuring out how to get the benefits of both at the same time within one model architecture.
And that's where Mixture-of-Recursions, this mauler, comes in as the potential unified solution.
That's the claim. It's built inside a single structure, a recursive transformer, which lets it tackle both things simultaneously.
How does it do the parameter efficiency part?
Well, it reuses a shared stack of processing layers across what they call recursion steps. Think of it like doing more thinking with less actual brain structure, if you will.
Getting more mileage out of the same components.
Sort of. It reuses parts to get more processing done without increasing the model size proportionally. That's the parameter saving.
Okay, and the adaptive computation, how does that work?
This is where it gets really dynamic. Moore uses these lightweight internal guides, the paper calls them routers. These routers dynamically assign different recursion depths, basically, how many thinking steps to individual pieces of the input text, the tokens.
So not every part of the input gets the same amount of processing.
Correct. It focuses the heavy lifting, the computationally expensive stuff like the attention mechanism, only on those tokens that are still being actively processed at a certain depth or thinking step.
That sounds much smarter than processing everything equally.
It is. And it has a knock-on effect for memory, too. It means the model only needs to cache the information needed for attention, the key value pairs, or KV cache, for those active tokens.
Which saves memory.
A lot of memory. And there's even a variation they mention where it reuses the key value pairs from the very first thinking step for all later steps.
What's the benefit there?
That further cuts down the initial processing time, the prefill latency, and the memory footprint right at the start when you feed input to the model.
Okay, so Moore tackles both parameter count and compute usage, and even memory, all within one recursive setup. How does it actually make those decisions? How does it route the tokens?
Good question. It comes down to the routing strategies. The paper mainly explores two. First, there's expert choice routing.
Expert choice. Okay.
Imagine at each thinking step or recursion step, there's a router acting like an expert. It looks at the tokens and selects the top few that seem to need more processing. So as you go deeper, the set of active tokens gets progressively smaller.
Narrowing the focus.
Exactly. That's the idea. And a neat side effect is that this method naturally ensures perfect load balancing. The computational work stays evenly spread out.
How do they get that router to work well?
They found that using a specific combination of techniques worked best. An extra training signal called an auxiliary loss, a sigmoid function for normalization, and keeping the router architecture simple, just linear. This combo apparently led to a really clean separation between tokens that needed more steps and those that didn't.
Interesting. And the second routing strategy?
That's called token choice routing. It's a bit different. Instead of deciding step by step, each token gets assigned a fixed number of recursion steps right from the beginning.
So token A always gets 3 steps, token B always gets 2, for example.
Something like that, yes. It can make some aspects of training a bit simpler because you don't have those step-by-step decisions.
But does it have downsides?
It can lead to load imbalances, where some processing units might get overloaded while others are idle. Usually they manage this with another kind of balancing loss during training.
And did one perform better than the other?
The paper's experiments showed that generally the expert choice routing the step-by-step one actually delivered better overall performance.
Okay, so expert choice seems promising. Now, you mentioned memory savings too with the key value cache. How does Moore handle that?
Right, the KV caching strategies are key. The main one is called recursion-wise KV caching. This directly links to the routing. It only caches the key value pairs for those tokens that are actually routed to a given recursion step.
So if a token stops processing after step 2, its KV info isn't kept around for step 3.
Correct. This drastically cuts down the memory needed for that KV cache, and it also reduces the amount of data being read and written, the input-output demands. Big efficiency gains here, both for training and for inference when the model is generating output.
Makes sense. And the other caching method you mentioned, reusing the first step.
Yes, recursive KV sharing. This one is simpler in concept. Take the KV pairs generated in the very first recursion step and just reuse them for all the following steps.
That sounds like maximum memory saving.
It is, and it can really speed up that initial prefill stage. But there's a trade-off.
Always a trade-off.
Well, sometimes. While it does reduce the number of attention calculations, the paper found it could sometimes lead to a slight dip in performance, particularly with that expert choice routing we liked.
Why is that?
Possibly because the later steps don't get fresh, updated KV pairs reflecting their deeper processing. Although, interestingly, they found it could sometimes help the token choice routing, maybe by giving those tokens access to broader context from the first step throughout their fixed processing path.
Complex interactions there. So these mechanisms sound good in theory, but what about in practice? What did the experiments actually show?
This is where it gets compelling. Across different model sizes, they tested from around 135 million parameters up to 1.7 billion. The Moore models consistently set a new benchmark. They achieved what's called a new Pareto frontier.
Okay, explain Pareto frontier in this context.
It means they found a better trade-off point. For the same amount of computational work during training measured in FLOPs, and often with smaller model sizes, more models achieve significantly lower validation perplexity.
Lower perplexity means better predictions, right?
Right, lower surprise, better predictions. And they also showed improved few-shot accuracy, meaning the models performed better on new tasks, even with just a few examples.
So you're getting the performance you'd expect from a much bigger, more expensive model, but with the efficiency of more.
That's the takeaway. Large model quality without the full large model cost.
And what about concrete numbers, like training time or memory?
They showed that using the same training data, more models could hit lower validation loss and higher accuracy while using 25% fewer training FLOPs.
Wow, 25% fewer FLOPs.
Which translated practically into things like reducing training time by 19% and cutting the peak memory needed during training by 25%. Real savings.
That's significant. And what about when the model is actually being used for inference?
Even bigger gains there, potentially. More boosted inference throughput, dramatically up to 2.06 times faster than standard transformers in their tests.
2 times faster.
By cleverly using something called continuous depth-wise batching. It basically keeps the GPU busy by efficiently scheduling tokens that are at different recursion depths. No wasted cycles.
That's a huge practical advantage for deployment.
Yeah.
Did they explore how to best share the parameters? You mentioned reusing layers.
They did. They looked at different strategies for which layers to share within that recursive stack. The one that consistently performed best, achieving the lowest validation loss, was called the middle cycle strategy.
Middle cycle.
Yeah, the idea is to keep the very first and very last layers unique to the model, but then share the weights among the intermediate layers in a cyclical way. It seems to strike a good balance between saving parameters and maintaining the model's ability to represent complex information.
Okay, and what about that adaptive thinking? Could they see it actually happening? Did it make sense which tokens got more processing?
They showed some really neat analysis on that. The way more allocated recursion depth, the number of thinking steps, really seemed to align with how semantically important a token was.
For example?
Well, Content-heavy words like nouns, people, or drugs in their examples tended to be sent through more recursion steps, maybe 3. They needed more processing. But function words like and, or even punctuation like ook, they often received fewer steps, maybe just 2.
So the model learned to focus its effort intelligently based on the meaning or role of the word.
It appears so. It demonstrates that adaptive computation isn't just random. It's learning to allocate resources where they're most needed semantically.
That's quite sophisticated. Is there anything else that stood out from the results?
One more really interesting capability they highlighted is something called test time scaling.
Test time scaling.
Yes. It means you can take a trained Moore model and just during inference time when you're using it, you can decide to increase the maximum number of recursion steps allowed.
And what happens?
The model can actually achieve better results, improve generation quality. It's like allowing the model more time to think or refine its understanding of the input before producing the output. Each extra step helps refine the token representations.
So a trained model isn't entirely fixed in its capabilities. You can push it a bit further just by letting it recurse more.
That's the idea. It adds another layer of flexibility at inference time.
Okay, so wrapping this up then, what we've really seen today is that Mixture-of-Recursions presents this genuinely unified approach. It's bringing together parameter sharing for size efficiency, adaptive computation for smart resource use, and clever KV caching for memory savings, all within one recursive framework. It really does seem to point towards more efficient yet still highly capable language models, delivering that high performance but potentially at a much lower computational and memory cost.
It certainly looks like a significant step forward in AI model efficiency. It addresses that core bottleneck we discussed right at the start. And maybe, to leave you with something to think about, what does this idea of dynamic token level thinking really mean for the future? If models could truly adjust their thought process based on the specific piece of information they're handling, rather than applying the same brute force computation to everything, how might that change how we design, train, and even deploy AI systems down the line?